Alright, hell yes. What we have here is material mechanics, and this might be a full class lecture. I don't know how long this is going to take. Give ourselves an hour, maybe even two. But anyway, what we're going to do today is go over shear. And I think shear is the hardest thing to understand when we're dealing with how things are breaking, tearing apart, and especially when we do the analysis of it using free body diagrams. So that's what we're going to really master, is the free body diagram. The other thing that we're going to master is, heck yeah, taking these free body diagrams. We got secant of theta. I mean, that's crazy. You know what I mean? Your brain explodes. So what we're going to do is really simplify the trigonometry. I think anytime you use trig, I mean, you got to go back to like really basic. Think like you're a caveman doing trigonometry. Because look at this, sine 2 theta is like, no thank you. But we can really, like, even that I can explain in 2 seconds. You know what I mean? Like, what's cosine of 0? That's going to be 1. Okay, cool. And then what's cosine of 90? That's going to be 0. But guess what? Like this graph is 0 at 45. So you just have to double it to get, hey, 45 times 2 is 90. Booyah, you get that 0. Anytime you work with sines and cosines, always find your zeros and your ones. And just know that if you're just working with sines and cosines, like, hell yeah, these numbers can only be numbers between 0 and 1. You know what I mean? You either have 0% or you have like 100% of what you're talking about. You know what I mean? So that's what this just oscillates from 0 to 100%. 100% being max, you know what I mean, in this case. But anyway, so that's just kind of a little taste, a little flavor of what we're going to go into. If that's something that you like, hell yeah, stick around and let's do this. Alright, so this picture we're going to look at first. This is shear, you know what I mean? And let's say, I know this isn't the picture, but let's say we pull this bolt apart. What we know from material mechanics is it's the area of this bolt right here. That area, when we pull it apart, is basically going to tell us its strength. And what we know about steel is we have a number for its strength. And this is the max stress. Lowercase sigma is the symbol that they use. They call it stress. That stresses me out because you have stress, strain. What the hell's the other S word? You know what I mean? I'll think of it in a second, but it's too many S's. Even though strength is an S word, I think this really helps you. Strain just thinks of change in length. So that's how I change that. Stress goes to strength. Strain goes to change in... Oh, yeah, shear. What we're talking about today. You know what I mean? That's 3 S words. They should be 4-letter S words. I mean, so... you know what I mean? So, yeah, we're going to be mastering this shear. We'll probably have to stick with it. But, at the end of the day, there's a relationship between the strength of a material, which is this lowercase sigma, which is usually called tensile strength. You know what I mean? So that's what it's called. Tensile strength, ultimate tensile strength, yield tensile strength. Just you know what I mean? A number that you throw out there, we'll just throw out 58,000 pounds per square inch, or 58,000 psi. So this number for steel, you can call it 60, whatever. You can call it 70. I don't really care. You can call it 40. Don't really care to me. Some of the books really kind of stick with this 58. Now, is that ultimate? Is that the most strength you can get at? I don't care. Is that yield? Is that when it's going to start to like pull like taffy? I really don't. You know what I mean? We're just like, who cares? But anyway, but that 58 is what we're going to be using. And if we know that steel has this property called strength, that it can handle 58,000 pounds per square inch. It can handle 58,000 psi. And so we just look at the cross area here. Let's say this cross section was 1 inch. 1 inches squared, because this bolt is hella, and it's like 1 1/4 inch, 1.5 inch, you know, diameter inch bolt. The area is 1 inch. You know what I mean? Area of a circle is pi r squared. You know what I mean? So if this is 1, hey, let's do some backwards calculation. We're going to go 1 over pi is equal to r squared, square root of 1 over pi. Hell yeah. I love doing this stuff. You know what I mean? So that didn't make any sense at all. If the area is pi r squared, oh yeah, so what's the diameter? Yeah, so this would be the radius. So we found the radius. Area is also pi d squared. You know what I mean? And if area is 1, you go 1 over pi, square root of that. So, nah. No, this is over 4. Yeah, holy Toledo. So you'd go 4 over pi square root. You'd find, there you go. So you either just double this number, hell yeah, and you get a diameter of 1.12. That's what we were going for. Square root of 4 divided by pi. Anytime you can use, you know, just off the top of your head, like square roots and stuff, it's always good practice. So hell yeah, if you have a diameter bolt that's 1 1/8, you know what I mean? Because 0.125, double it is 0.25, that's 1/8. You know, you got to get, anytime you're using math, you just strengthen up on your decimals, on your fractions, on your pies, and on your sines and cosines. Anyway, so hell yeah. So 1 1/8 bolt in diameter will have a 1 inch area, and how much pressure can you put? You can tug on that bolt 58,000 pounds. Well, what's 58,000? Well, an empty semi. You can hang an empty semi with a 1.5 inch bolt, 1 1/8. You know what I mean? A full semi, hell no, that bolt's going to break, and it's just going to break right there, and it's going to break. Okay, but we have this other property that we know. Throw some more time on the clock. We have this other property, I mean, that's just pulling this bolt apart. But we know, just from physics, that we can actually, you know, put a force here. We can squeeze this bolt sideways like you're slicing it. You know what I mean? Like you're just like ripping it in two this way. That's what we're doing, shearing. You know what I mean? Like one part's attached to a trailer and the other part of the vehicle's over there, and you're just pulling it apart. You know what I mean? You're using this as a pin, and it's still going to break right there, but we're dealing with shear. Now at the end of the day, if we're talking steel, it's just half. It's just half as strong. So this 58,000 goes down to 25,000 plus 4, 29,000. You know what I mean? So this 28,000 goes to 29,000 psi, and just call it lowercase sigma. You know what I mean? So anytime that you're just like, whoa, look at this. I've identified the area, but I'm going sideways. I'm perpendicular to this cross-sectional area. So if I pull this way and this way, hell yeah, that area is like, the face of this area is facing the direction of the force. But in shear, this area, the direction of this area is not. It's perpendicular to the force is going that way, and this area is the face of this area is going that way. So this is what we call shear. Now at the end of the day, just identify that you have something in shear, and then just half your tensile strength. For steel, this works pretty good. You know what I mean? But at most, it can be like 0.7. And in this video, we might explain why that 0.7 is the case. Because what's the inverse of 0.7? 0.7 inverse is like 1. Well, I don't know if I'm going to explain, but yeah. So if in shear you're only getting 70% of the juice, that means it's 140% stronger in tensile strength. Tensile strength is 140% stronger, but if you're only getting if you're only getting 50% of the juice in shear, tensile strength is twice. You know what I mean? So that's kind of what we're going to be looking at. Okay, hell yeah. So that was just a little introduction about what the hell shear is. And how, yeah, it's really easy to just pull stuff apart, identify the area, that makes sense. But shearing, you're like, oh, okay, I gotta have to have, like, you know what I mean, two forces going against each other. But anyway, and I think that the first thing to do is, hell yeah, let's do a free body diagram. Because if you say there's a force here and a force here, well, isn't there 2 times the force on this area? And the answer is no. Just like the fact that, hey, if I pull on this bolt with 58,000 pounds, and then I get somebody else to pull with 58,000 pounds, isn't this bolt saying twice that? And the answer is no. The answer is no. And you're like, well, why is that? And I think this is where this video actually gets cool. So we're going to add some more time on the clock. So the reason this video gets cool is because, let's take this bolt again. Hell yeah. And it gets cool because what do we know about the known universe? Let's say this bolt is just floating in outer space. And you just said you put a force this way. You know, of whatever, 58,000, doesn't really matter, but you put a force that way, what's going to happen to this bolt? It's going to move that way, and it's going to accelerate that way. So if this bolt is initially at rest, 0 meters per second, and then you put a force to the right on this bolt, well, guess the hell what? It's going to move that direction based on F equals ma. Newton's law that says, hey, its acceleration, this bolt does have mass, so the acceleration is going to be that force that you figured out, whatever it was, divided by the mass. And let's say it's 1. Hey, every second this thing is going to be going 1 meter per second faster. You know what I mean? So in 1 second, it's going slower than walking speed, or 1 meter per second. That's walking speed. Every second it's going walking speed to within a minute, this thing is just going to be going real fast. Okay, so that's the deal here. But let's say we know we're putting a force on this bolt of whatever, but we still observe that it's stationary. Well, then what the hell? This isn't balanced. So there must be a force this way. If I say I'm putting a force to the right on this bolt in outer space, and it had no velocity, and it continues to have no velocity, the only way that bolt is going to stay stationary is if there's an equal and opposite, equal forces pulling on this bolt both directions. All right, so that's mind blown right there. And even if you're graduating this year in physics and engineering, you'd be like, ah, damn it. You know what I mean? I wish I had videos like yours, hell yeah, in high school. Anyway. All right, so that'll blow your mind. And this concept will be very crucial to shear. Why? A little bit of foreshadow, because look, we got 4 arrows now, and you're like, what the hell? We're only like pushing this way and then loading it that way. Why is there 4 arrows? Well, we're gonna get to that. We're gonna get to that. Okay, but that should take care of, like, hell yeah. Oh, no. So now we have to do free body diagrams, because we just did one. We isolated a bolt, and it's floating in outer space, and we put 2 forces on it. So now what we want to do is we want to take this part of the bolt and separate it from this part of the bolt. So from our picture, just do this, and we're just going to look at this part. Okay, hey, well, this part has a force on it. That didn't change. Okay, but now just pretend like we isolated it into outer space. Like, hey, what? And then when this bolt was just, when we initially saw that, pretend this bolt's a bridge, and you're going to do a free body diagram on a bridge or anything. You know what I mean? You can chop away a section, identify a force on one half of it, but at the end of the day, is that bridge moving down the highway? No. The cars are moving down the highway over the bridge. But so this bolt is totally stationary. And then so when we go to cut it, and then we still have this force on that face. Well, again, it's just like the original thing where I have a bolt in outer space and I put a force to the right. Well, we're observing that this thing is still stationary. So Newton's laws say, hey, if this is the x direction, you know what I mean? Forces in the x direction, the sum of the forces in the x direction, equal the mass of whatever it is, times the acceleration in the x direction. But we're observing no acceleration. So all the sum of the forces, and I should have wrote this better, sum of the forces in the x, we observe no acceleration, so this has to be 0. But guess what? We have a positive force in the x direction. So our x direction, so if we sum the forces, we're going to have this F is equal to 0? So we have to say F, minus something. I'm just going to call it a letter. I don't even know what letter to call it. But I think we're just going to call it N. Booyah. And I think that's what the physics books use too. Because you have, on this surface, what do you have? You have a normal force going in the opposite direction. Or, it doesn't even matter. Like, this is where if you drew it this direction, well, now you have F plus N equals 0. Adding two positive things ain't ever going to get you to 0. So N, by looking at this, N must be equal to negative F in this case. Now, if we drew it this way, where N is going in the negative direction, this is the positive x direction, then we would have F minus N is equal to 0, then F is equal to N. Booyah, check mark, you know what I mean, check the box. All right, and we could do the same thing over here. This part of the bolt, F, so we have in the x direction, sometimes I just do that. Sometimes you can be like sum of the forces in the x is equal to 0, because we're already observing stationary. So we're taking Newton's equation of sum of the forces in the x is equal to mass times the acceleration in the x, and we're just saying, hey, nothing's moving, baby. You know what I mean? We're working on bridges. We're working on static things on Earth. When we're not in the physics lab looking at particles move across the room. Okay, so this equation just becomes sum of the forces equals 0. So if we pick a direction, this x direction, so we have negative F, and in this case, this is our N. You know what I mean? Just a random N, okay? And in this case, we have negative F plus N is equal to 0, and guess what? N is equal to F, check this box. And we can even say this is N1 and this is N2. So let's do that. N1, 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 N2, N2. F is equal to N1, and F is equal to N2. And so we're just showing that these two forces, obviously we've already identified that they're equal. We're going to say this is F1, F2. So F1 is equal to F2, and N1 is equal to N2. All right, so hell yeah. And then, I went through, that's why I'm making these videos, because I went through college without these building blocks of just being like, whoa, no one taught me the free body diagram from the floating bolt in space analogy. I had to come up with that one on my own, but it just makes sense for anything. So if you have a bridge and you're just like, hey, I'm gonna take this segment out, so now I have this, and it's like one of those bridges where this is just a cable. You know what I mean? So I take this cable out, and I know this cable can only take tension. So then I go like this. You know what I mean? You got a tension there and a tension there. And because I isolated it, and now to me, this thing is floating in space. You know what I mean? And let's say just on this side of it, I knew that there was, like I put a meter here. You know what I mean? Well, whether it's a scale or like a little springy thing on a scale. You know what I mean? And I knew the tension on this side. Well, if I drew a free body diagram, cut this little chunk out, I know from observation that this thing isn't moving. Therefore, the sum of the forces always has to be 0. I identified one force, so I identified this force. Well, guess what? I have to identify an equal and opposite force that's going to be the same. If this is T1, this is T2. T1 is equal to T2. Now, just explaining it just like real fast and just being like, oh, whoa, this is cool. Now I have the tools to cut any section of this bridge, you know what I mean, and be like, oh, you know what I mean. Now I can do that, knowing that you're using my method of being like, hey, this bridge section, just pretend like it's floating in outer space. Okay, now we kind of shift gears. Throw some more time on the clock. All right, hell yeah. So now we kind of shift gears because we have to figure out this thing in shear. So what we're going to do, grab another sheet of paper. And so we're gonna so what this square right here, and it doesn't matter if it's the whole damn thing. You know what I mean? Maybe that would make more sense. So we have this bolt. And let's say we just take a chunk like this. Okay, cool. So that's our chunk. We're saying we have a load on this side, we'll call it F, and a load on this side, and we'll call it F. Okay, well, let's do that. Let's do that free body diagram FBD. And we're gonna take this chunk out of there and then just move it right here. Okay, now what do we know about this chunk? Oh, and maybe we shouldn't do that. Maybe there is a third confusion, because we're like taking a slice out of this, or an element. Maybe we don't want to do that. Maybe we want to do what we've been doing, is like, hey, let's go halfway, like right to there, and we'll take a chunk out on this side, and then a chunk out on this side. Because now we know that we have a force here, that means we have to have a force here. Okay, right? You know what I mean? Because if these are in the y direction, the thing ain't, you know, if you just had this force, it's going to go to the ceiling. And if you have this force, you know, that's going to balance it out. And over here, you have this downward force. And then so you must have an upward force that's equal and opposite. Cool. Okay, so now we're getting somewhere. And all right, hell yeah. Oh, and this is tricky because this face is this is that face right there, and this face is that face. You know what I mean? Because this face is pointing that direction. That's that face. This face is pointing this direction. That's this face. Okay, and I don't think that's actually helpful. I think that just probably confused everyone. But no, I think if you chop this out, you first say, hey, I'm going to do this. I'm going to here. I want to know what's happening on this face, and so we have a force right here, and then we have this the other chunk over here. So I'm going to say on this face we have an upward force, and that really is exactly what's going on here. And then when I cut this section out, I'm cutting the element out plus what it's attached to, and I know that we have an upward force. So on this face I have a downward force. So booyah, I'm learning on the fly. But anything to make this free body diagram, because what's going to trip you up in all sciences is a friggin' sign change. You know what I mean? You just lost a sign, you know, taking one part of the thing to the other side of the equation. And then there's so many roadblocks in science where you're just like, in physics, if you're just like, whoa, I have to choose between a positive and a negative. Does this arrow go up or down? And it just makes your mind melt. And the only way to actually have a foundation is to go back to something that's really simple, like the bolt floating in outer space. You know what I mean? Where you're just like, oh, okay, if I have a force this direction, I must have a force that direction. You know what I mean? Those simple concepts are the only way to actually build upon your knowledge. You know what I mean? And so I spend a ton of time going back to really simplistic basics and then seeing how that just really helps learning more complicated things. Okay, so hell yeah. So now we've identified that we have that little chunk, and yeah, we didn't, because this, they're just like, hey, this is a small element, and even that's too confusing, because let's say, I mean, is a small element that, or is a small element so microscopic, like that's a molecule, that's a molecule, that's a molecule, or is this whole thing just one molecule? You know what I mean? Also where your mind might bleed. Okay, so we've identified that we could take the small element and just make it big as, cool, but we're gonna get back to maybe well, no. Yeah, this element is perfect, because we're taking a huge element, and because here's the other thing that goes from this free body diagram to this. This is not a free body diagram. These are not forces. These are shear. So we talked about how lowercase sigma is kind of tensile strength, and we get that. But also shear is all, and it's in PSI. You know what I mean? So it's pounds per square inch. So if I have an area in inches squared, hell yeah. And I have PSI, So even right here, you can find a relationship. So if I have PSI, which is pounds per inches squared, and then I have area, which is inches squared, it looks like I multiply those two together to get pounds. So this is one of those that I love in physics, is the units are the equation. You know what I mean? If you start with one set of units that says pounds per square inch, and you multiply by square inches, well, booyah, you automatically get the relationship that is in pounds. So what we did is we took that this was 58,000 pounds per square inch of steel. We identified that it had 1 square inch of area, and we multiplied 58,000 psi by 1 square inch, and we got 58,000 pounds. We can pull that way and that way on that. Excellent. All right, so now we have to, like, I'm trying to, you know, clean up the house before we, you know, open, you know, yeah, my bedroom. Holy Toledo. I'm a hoarder. Anyway, so what we have, so we've identified that we took a big element, and we could, at least, on this case, we found the force. We found the force on this huge-ass chunk, and the force on this huge-ass chunk. So let's draw that in, and let's go back to our bolt. And so it's circular, and we're still going to say it's a 1-inch bolt. But hell yeah. So we have our bolt. We've identified that that there's a, on this bolt, there's a force up, a force down, and then there's a force down, and there must be a force up. So look at this. Now we have three body diagrams, and then you have our little chunk, and it's still, you know, we can call it a circle too. So on this chunk, if this is going down, this must be going up. So we have a force on that, and this force going down. Now, how they get to stress is they say, well, hey, this force is acting on that area, and this force is acting on this area over here. So now, when we were talking about tensile stress is equal to... tensile stress times area is equal to force. That's probably a horrible way to write this equation, but that's probably the best. Start with your strength, multiply by area, and you get force. So let's rearrange this, and strength is force divided by area. So if we wanted, if we only put like 100 pounds, and we know we have an area of 1 inches squared, well now, and 100 over here, because the thing's not moving in outer space, not going that way. You know, it's not particle physics. Anyway, so hell yes. Think stationary, it's got 100 pounds. 100 pounds is acting on the area. Booyah, we have a, so we have 100 pounds, area of 1 inch squared. So we have 100 psi. Cool. So the stress, that's where, yeah, now this is stress. Because that's the other thing. Strength, like 58,000 is how much this can hold, but obviously you can only put 100 on it and it's still doing something, you know what I mean? And it's not getting up to that breaking strength of 58,000, but it's getting up to 100 psi. So between 0 and 58,000 psi, you have every range that steel can experience. It can experience 100 psi, it can do 1,000 psi, 10,000 psi. Okay, cool. And then so that's where they use this word stress. So it's just one of those you'll have to get used to. But I always think stress is strength. You know what I mean? And especially when you're talking about that ultimate, you know what I mean, that ultimate 58,000 or that yield strength when it turns to plastic. Yeah, if someone's getting fired if your steel's turning to plastic. If you reach that yield, definitely if you reach that ultimate, that's just when it breaks. Cool. All right, so we have identified this little chunk, and but now we've identified that the force isn't in the direction. The area is facing that way, and then if we pulled on it this way, those would be in line. But our force is perpendicular, so we identified that we have this term called shear. We are cutting. We are cutting this bolt apart this way. That's a cutting motion. Not just pulling tension or compressing until it pops. But yeah, you can only compress steel so much too before it breaks. That we'll see if we get into, because you do have this element that even if you're pulling on a bolt, you are shearing it. And then, yeah, let's introduce that right now, because we have to make this video just a little bit more exciting. Because you're just like, what? No, if I'm pulling 100 pounds this way, 100 pounds this way, all it's experiencing is tension. But it's like, no, it's not. Because let's say this bolt is really long, and I draw a line along this bolt like that. And I cut this bolt in two and then glue it back together. I think that's kind of what the engineering books do. They're just like, hell, let's say I glued these two pieces of steel together along a 45 like that, and now let's say I'm pulling up on them. Well, it looks like you're shearing them. You know what I mean? It looks like this, but it's just your surface area is much larger. So there you go. So hell yeah, you have a large surface area, and now you're pulling in shear. So now pretend like you didn't cut this and glue it, but every molecule to a degree is so there are molecules along this thing, you know what I mean, at this angle. There's molecules along here at this angle, you know what I mean? So I mean, literally you can pick any different line of molecules through this, and there you go. So there is, and we know that if you do shear something, it's only half as strong. You know what I mean? As low as half as strong, which is crazy. So so the second you orient something, let's say you orient it like at a 45, well, hell yeah, this area just grew. But let's say it only grew by the square root of 2. You know what I mean? You got a 45-degree angle. This is 1. Now you have 1.4. So your area increased by 1.4. But now it looks like you're pulling in shear. So if you're pulling in shear, you know what I mean? Well, maybe and your shear is half. You know what I mean? So I'm doing a very poor job, but this is where it happens. So it's like, let's say all this, even at a 45-degree angle, let's say none of it's actually going, it's all going in shear. So now you have 100 going just on this 45. Or I mean, you have 100 going on this 45-degree angle, but your area increased. But you know that if you're in shear, it's only half as strong. So it would be like doubling it. So now you have 200 over an area of 1.4. So I mean, sorry. You have 200 pounds divided by an area of 1.4 inches squared. Where here you just had 100 pounds divided by 1 inches squared. So here you'll generate 100 psi, and in here you will generate 200 divided by 1.4, you'll generate 142 psi. Now, that's not 100% correct, because 100% of this isn't going in that direction. You only get a square root of 2 over 2, or 0.707, or the sine of 45, or the cosine of 45. You pick, but if you're at a 45, your normal force is now reduced too. So that 1.4 times the square root of 2 divided by 2, it's back to the same. It's back to 100 psi. But there are certain properties, you know what I mean. So, but now, like there's going to be certain properties that can't take any tension, you know what I mean, or can't take any shear. They can take a compressive load, but they can't shear. Like sand. Like I was doing this as an example, and this is a really good example to explain this. I think this is where my videos can actually, stay exciting, is because I jump around a lot, but it's just all going towards the full explanation of what is shear. Because if we just have sand galore, and we just have a 1-foot chunk of sand here, well, this bowling ball, it's not going nowhere. Observation is stationary. But and the sand did not break. So now we're in compression. The normal force against the earth. We got to put more light in our camera. All right, hell yeah. So in this example, you know what I mean, we have all these molecules of sand, and they can take a ton of force. You know what I mean? Their force and compression is real strong. But if we draw like a diagonal line, you know, through this sand, like at a 45, well, now these particles of sand want to slide along this path. But, you know, as long as we have this sand kind of blocking it like an ocean of sand, well, it's not going to slide along that path. It's pushing against there. But, you know, like sand, it can't take hardly any shear strength at all. So in this diagram, let's say we remove the sand by digging. And once we remove enough of this sand to where you basically have a small column like this, well, now this small column can fall that direction. And because these particles of sand can't hold the weight, I mean, because you have a downward force here, yes, but at this angle, if we do a free body diagram, and this is even good for me. So now we're going to take that. If we take that bowling ball in this chunk of sand at a 45, and now we say, hey, we used our observation, and it's not moving, like zero velocity. It's not moving. We have a downward weight. We're going to say this is the weight of the bowling ball. Okay, cool. And we're going to say the sand is negligible. It doesn't have any weight. But now here, if you have a surface, so now you have this kind of surface, you know, and I know you can't see it in 3 dimensions, but you can only have a normal force to this surface, and you can only have a shear force. And we're going to call that V. So these are the only 2 forces that can hold this this W up. And let's see, I drew this wrong because you would have the normal force going that way. Since we're just drawing the free body diagram. I was thinking we're drawing the element. But if we draw this, so you have a normal force going up. And if we have this normal force going up, this is where it's just really easy to go back to hey, this thing is in outer space. We have a downward force. We have an upward force to balance that out. Cool, I see that. But now, if this force is at an angle, it's actually going, it's got a component to the right. So I drew this wrong, and this is now going to the left. So there you go. So, I mean, if we just said this is 100, and this angle is a 45-degree angle, we could figure out that, I mean, I think we can just do this real easy because these both have components. I mean, whatever V is, it's V, you know, sine or cosine, it doesn't matter. But like depending on where you draw it, if I draw this angle right here, then it's going to be this upward part that's in this direction is going to be. If here's your angle, this is the sun shining on the sine. So that's what I do there. Cosine is adjacent. So if you have your angle, this is your sun shining part, and that's your vertical. So you're going to have V sine 45, and this is going to be upwards. So this is going to be the y direction, and then this is going up. So let's say your angle's right here. I mean, I drew the angles at 2 different places, but this is also going to be n sine 45. But it doesn't even matter, you know. You just have, and that's 0.707, or the square root of 2 over 2, if you want to know that. But 0.707 n, 0.707 v, and then minus w is equal to 0. And then towards the right, you have negative 0.707 v, and then plus 0.707 n. So this is equal to 0. So this equation says that v is equal to n. So there you go. So now you have n is equal to v. So now you're going to get square root of 2v minus w is equal to 0. So is equal to w. So v is equal to w divided by the square root of 2. So 1 divided by the square root of 2 is 0.707. So there you go. So V is equal to N, which is equal to 0.707 W. All right, so we just used a free body diagram to, if we say this is 100, you know what I mean, this is going to be 70.7 and this is going to be 70.7. All right, but that's important because we said that sand can take hella force, you know, in this downward direction in compression, but in shear it can hardly take anything. You know what I mean? So now we're saying that we have 70 pounds in shear just on this 45-degree angle. Well, it can't take anything. You know what I mean? So it's just going to slide. So this section of sand right here is going to slide this direction against this section, because you would have to have this shear force like that. That's what this free body diagram says. Hey, we chop this out, and we're just going to say it's floating in outer space, and we observe that it's not moving, which is incredible. Because, but you would have to have a shear force of 70 pounds against all these molecules of sand, but we know sand can't take shear. So in this case, we probably would see a collapsing. And if you move this sand away, hell yeah, you're going to collapse that column of sand, because, you know, if you get it wet, maybe it has just enough shear. You know, if you make actually like a sand castle, put a bowling ball on it, but if you did see it crack, it might be at this 45-degree angle. It's not going to be you know, angle straight across, you know, unless that sand is actually just like, I don't know. But that's a good example of a shear failure at 45. Now, if sand could take some shear, you know, it's not going, this whole thing's not going to slide on a very steep angle, because now you just increased your surface area. So now your surface area and your ability to hold shear is just a lot more gluey. But if you, so there's a perfect place where at a 45-degree angle, you get max amount of force in that shear, and your surface area only goes to the square root of 2, which is 1.4. So your surface area increases from 1 to 1.4, which is a significant increase. But that's going to be your magic. That's why things fail at a 45-degree angle. All right, hell yeah. So now I'm going to cut some fresh paper. All right, hell yeah. And I got to challenge myself, because we need to move on to some of the other papers. Because we're going to go from, hey, we're just shearing this bolt apart, to this, we're going to twist. This is the classic, hey, I'm going to twist a piece of chalk. And guess what's going to happen to the chalk? It's going to break, and it's not going to break. It's not going to break like this along a perpendicular surface. It's going to break on a helical surface. But this is a brittle material. So not all materials will actually break on this brittle 45-degree helical surface. So keep that in mind. But this is a good introduction of what's going on. All right. So hell yeah. So we're gonna move from this bolt. Identify a little chunk of it. Know that we have a force going up and a force going down on that element. Here, when we twist it, because we're twisting this, and this brings up, let's say I have like a wrench on this pen, and you know, just a big old tire iron connected to this pen, and I'm just really giving it hell. And then my objective is to keep it from moving just by squeezing, you know, just right here in the pen. Ain't happening. If I throw a tire iron and bolt it to this pen and then give it hell, there is just no force that's going to be able to keep this pen from twisting between my fingers, or you know, even in a clamp, it's going to be really easy to twist this pen. But if I counteract, let's say from this end I just twist it this way, and over here I actually glue on like an arm and then hold both sides of that arm. Well, now any twisting motion, I can easily, you know, prevent this pen from twisting. So that's what happens when we have a cylinder. This arrow is a right hand arrow, so we use the right hand rule. We stick our thumb in the direction of these double arrows, and this means that this side is rotating this way. Now, over here, we got to flip our hand palm up. Finger goes into those arrows. Now, this side's rotating this way. So if I keep that in mind, this cylinder, and I kind of have a cylinder here, this cylinder is rotating this way on this side's rotating this way. So now I have something like this. I have something gripping the cylinder over here, and now we're going to rotate. But in this is a statics problem. What you're seeing is, you're seeing like, hey, I'm trying to rotate it this way, and this hand is trying to rotate it that way. But what happens in our bridges, in the problems that we want to do, is that we see no motion, and that's important. And now that you already have that, kind of in the back of your mind, we can tackle why there's 4 arrows on both of these. Okay, so I'm going to put this aside, but we're going to get back to it very quickly, hopefully shortly. So we've identified that, heck yeah, we took out a chunk. We said we had a force. Now I got to figure out, force down on that side. Yeah, this is tripping me out, because if I take an element out, I almost don't know, it's like I got to say that, hey, oh, this is really going to help me. This is actually going to help me. So if I take this element out, just right there out of the middle, I can say, hey, this side, this face is still connected to the larger bolt over here. Cool. This is wigging me out. But then this face is actually connected to the larger piece of the bolt over there. Okay, so if I do that, this face has this load on it, therefore this downward force must exist. So I must have and we're going to call it V for our force, but it's just a letter. We could use F, we could use P. Okay, and then this face was connected to the bolt over here, which saw this load going down. That's the load. This is the load. And now we have to counteract that right there. Cool. So now we're going to hopefully get quickly into the concept of why there's 4 arrows, not just 2. And it's because these arrows are not in line. It's because, let me rephrase it, it's because this is a 3-dimensional object. So yes, if we sum the forces in the y direction, let's say this is the y direction, they're going to be equal to 0. And we say this is V1, this is V2. Let's do that. So we have negative V1 plus V2 is equal to 0. Therefore, V1 is equal to V2. Okay, check, check, check. You know what I mean? We got it. You know what I mean? And the forces in the sum of the forces in the x direction is 0. Well, there's no forces, so 0 is equal to 0. Again, check. Okay, but this is cool. So we're going to say, hey, let's say this lid is floating in outer space. And over here, I put a force on it this way. And then over here, I put a force on it this way. Well, what's going to happen to this lid? It's going to move. And it's just going to spin. So we're doing that good by, hey, taking our elements, pretending like they're in outer space, and now you just said you put a force this way and a force this way. I mean, we definitely have a spinning force. We're going to get some omega, but we don't, because our original observation of this bolt is that it's stationary. Let's say it's a bridge or something. We observe the bridge is stationary, so now what has to happen? Well, you have to have something to keep this from rotating. So if we said we had a force this way and this way, that's rotating it this way, well, we must have to have a force that way and that way to keep it from rotating. And that's exactly what we have. And we can use the right-hand rule again, too, because we have, you kind of swing your fingers in the direction of these arrows, and then, hey, my thumb's pointing up. So I come over here, swing my fingers in the direction of this arrow, my thumb's pointing up. Okay, cool. So now this is generating, and in physics, for our sign notation, anything that's coming up out of the page, or thumbs up, is going to be a positive notation. So this is a positive rotation. Anything that wants to rotate, and it's counterclockwise. I think memorizing it as counterclockwise that's totally arbitrary for me, but I'll continue to be like, hey, thumbs up, right hand rule, positive. You know what I mean? And then just be like, oh, that is counterclockwise. Cool. So counterclockwise. Now, so we have to have an equal rotation the other direction. So we're going to go thumbs down, and on this top surface, we're going to put an arrow that way. Now we're going to go thumbs down. On this bottom surface, we're going to put an arrow that way. Now, I think using your thumbs up, right hand rule, we're just saying, hey, I'm like driving it like a car. Hey, this force is going that way, so I need to go over here and then do the opposite. So these forces go that way. And then booyah. So now we have our V1, V2, V3, and V4. And guess what? We have a new direction, and now we're going to call this the x direction. Forces in the x equal to 0. So now we have V3 minus V4 is equal to 0. So now we have V3 is equal to V4. Now, what's the equation that relates all this is your moment equation. We're going to say that this is the origin, and moment is when you do have a torque. Because, like let's say this Play-Doh is rigidly, like glued to this sheet of paper, and then I'm going to put a force this way and this way. And this lid can resist that force. Cool, I just imparted a torque. You know, just like trying to undo the bolts of your car, you're putting a torque on it and then it moves. Or you're tightening them, it's moving, and then it stops moving. So you're imparting like 100 pound-foot torque. Cool. Alright, so that's torque. So any forces on a non-moving object is not moving, imparts a torque. And this torque is, so V1 is equal to V2. We're going to say that this full distance between is D. We're just going to call it D, or 1. You call it 1. Because now we're going to say, hey, the torque from the origin is half of D, or just 0.5. So now we have 0.5 times V2 in the positive direction, plus 0.5 times V1 in the positive direction. And this is our moment. So we're summing the moments. And we're observing that there is no rotation. So the sum of the moments should be equal to 0. And we've just identified V1 is equal to V2. We just identified that we have... Alright, hell yeah. Now this is the worst. It's when my camera shuts off. It shuts off after every 10 minutes. But we only got to this far, so hell yeah. So if an object is at rest and not moving or rotating, the sum of the moments has to equal 0. And so the first thing that we did is we identified V1 and V2. That's a positive moment in that positive direction. It's a positive torque. You know, if we're torquing our car, or bolt on our car, we're going that way. So then we have to have the other torque go in the opposite direction. I don't know how far I got, but we have to pick an origin. So we're going to pick the origin right in the middle. And I'm going to say, hey, we got to pick a distance. Just one of these faces I'm going to say is D. This is also D. But we're just going to call it 1. You know what I mean? So if the distance is 1, the torque due to this force over here is just half that distance, because the origin's right here. The diameter is 1, kind of the radius from here to there, that distance is a half. So what we started to do is say, hey, or we'll start with this one. 0.5 times V2 positive, 0.5 times V1 positive. So we've identified that we have a torque that's going to try to turn it in that positive counterclockwise direction from V2. V1 does the same. So we have 0.5 V2 plus 0.5 V1. Now, does this equal 0? Hell no, because these are both positive forces, and so this can't be the case. So that's why we have to have, there must be some other forces. And you can't just have one of these. If you just threw in V3, sure, you could counter it by having V3, but then your sum of the forces in the x direction, well, you would have V3, but then nothing to counter it. So you do have to have a V3 and a V4, and then those are going to counter each other. So now you're going to have this half of V2, half of V1. Half is just the distance from the origin. So torque is measured in distance, or moments are measured from distance from the point you're trying to figure out the moment from, distance, and then times force. So we have 0.5 times V2, 0.5 times V1, minus, and see these are the opposite, V3, 0.5 times the V3 times 0.5 times V4. Now this is equal to 0. And now we're, what I did is I just said, hey, V1 and V2 are the same, so we're just going to call this V1. We're just going to call this half. So we got half of V1 plus half of V1 is V1. V3 is equal to V4, so we're just going to say negative half of V4 minus half of V4 is just minus V4. So we get this relationship between V1 and V4. Those are the same. So cool. So we just did a huge calculation just to show that, hey, there's two other forces and they're countering, and because the square, this little small element that we drew is symmetrical, these are going to be, so V1 is equal to V2 is equal to V3 is equal to V4. So at the end of the day, that is where you get these other two forces. And it's because you can't just put a force on this element, it'll just turn. So you have to have counter forces like holding it in place. And that is bizarre. I think. I mean, if you're trying to shear something this way, just the fact that if you're doing it perfect where this thing isn't rotating, because if you're putting a force this way and a force this way on a three-dimensional object, you should just be rotating it. But if you're actually holding it between your hands, if you're putting this force in, I'm also, putting this force this way and this force this way. I'm actually putting those forces in. I wish this demonstration needs 4 people, but if I pull out on this balloon, this is tensile strength. But if I do a force up and a force down, what happens is this? It just spins. You know what I mean? I will never get the torque on it unless someone grabs here and then pushes that way, and someone grabs here and then twists it this direction. Because this direction is the negative right-hand rule, and I'm trying to go this direction, which is the positive right-hand rule. So I'll make a video on this where I hold it and then someone else holds those other 2 points up there. When I put a force up and down, because look, it just rotated. So when I do so even just looking like right here, this should not rotate. So if I do a force up, someone's got to do a force that way, and then the center of this won't rotate. Okay, hell yeah. All right, so I think we did it. I think we took a square element out of this bolt. So now we can move on to kind of what we want to do. We want to look at, and we don't have to, but we want to look at, I think it's easiest to look at what, this is going to be called pure shear. You know what I mean? When you torque something, there really is no definitive change in length this way, like squashing it in while you're twisting it, or like enlarging it while you twist it, because there just isn't. There is no properties that, hey, if you twist something, whether these molecules are going to squash in or stretch out. And so what you're left with is the only thing that's holding the strength is, or if you take a square element, I don't want to say things that aren't true, but if you take a square element, you're gonna get that box where you have 4 forces, and so we're gonna generate that. This is torque, so this is a force times distance. Let's say this is our distance. I know it's the radius, but we're just going to use small d for distance. And I don't know where I was going with that. But this torque can also be generated by putting a force. Oh, let's see. So we're going to put a thumb in the direction of the torque. Fingers go that way. So we could put a force over here, and then we could put a force over here. Cool. And if this is a distance d divided by 2, there you go. So now we have a torque. The torque on this side is going to be force times distance, d over 2, plus f d over 2. So then you're just going to have a torque of F times the diameter. All right, sweet. Or two times the radius. Anyway, I don't think that's where I want to go with this. But again, we talked about torquing, you know, putting mechanical advantage on this pen, and then just trying to hold the rotation over here. It just ain't happening. So the same thing in this. If this is solid steel, the molecules inside along the line, you know, along the center of this, can't hold any torque. You know, only the rigidity of these outer layers can hold back the most torque. Because we said, hey, if we impart a torque here, what you'd really want to do is weld on some sort of metal bar, and then put your hands right here and your hands right there. Well, in essence, these molecules of steel are also trying to, like, not move. You know what I mean? So we're going to, again, observe that this thing is stationary. And we're imparting a torque on both sides. And so if we do that, so let's do some free body diagrams. I think that will actually help me too. So we have this setup, and we're just going to say we have a downward force here and an upward force there. So that's going to, damn it, I did not draw that right. So we are going to go up here and then down over there. That's going to be this torque with two arrows. Okay, so now we have a force here, a force there. And to counteract it, and over here we have a force down, you know, right hand rule, and then a force up. Okay, so we kind of just did the opposite. So this face right here goes down, this face goes up, the opposite face goes up, that face goes down. So there you go. Twisting this way, twisting that way. Alright, so if we do crop out a slice, and I don't know if this is a good way to do it, but let's take a huge slice. So now, and then we're going to put that slice down here. So if we take out, if we do a free body diagram right here on this little chunk, we're going to draw it here, force, force, and that means that right here has to, and we have a torque this way. So this thing's going to have, like, if we just isolate this in space and all we do is put this force and this force, it's going to spin. It's going to spin with an omega. And we know that can't happen. So we have to counteract it, and we can use our right-hand rule. This force is going that way, so hell yeah. So this force has to go this way. So we're going to have an up. We're going to have an up there and a down there. Booyah. So we did it. We did the free body diagram. Now this thing visually ain't moving. And that was a quick way. So now what we're saying is that this face that we just put this on is that face. You know what I mean? Because we could just stretch. There's no difference between taking the slice right here than taking the slice right there on our object. And I think, I mean, for this video, that's going to be the bread and butter. I think that's the coolest thing I learned just by making this video is like, whoa, never thought of that. That I can just circle this portion and know that this face has the same identicalness there. So we got a force up and a force down. So now we're going to come over here, do that free body diagram. We're going to go this way. And we're going to say up, down. Now this one, hell yeah, right hand rule is going to spin. So it looks like it's going to be spinning this way with an omega, but that's not true. This is a bridge or something important, and it can't spin. You know what I mean? We built it, we welded it together. There is a torque on this member, but it can't spin because it's not a shaft of a car. You know what I mean? We're just trying to support something. So the only way we can, this is going to spin this way with our thumb's going that way. The only way that we can counteract it is if our thumb goes this way. So now we're going to come over here and we're going to go down and then up. All right, hell yeah. And now we can say that this face And so what we did was we did the free body diagram right there, but we're just going to extend it and say that, hey, these faces are the same. So now this one is up on that side, and then if we go to the opposite side, it's down. So there's our element. You know what I mean? So that's pretty cool. And this is a huge chunk of element. But what they're getting at in the picture is, and man, I hope I did this right. Yeah, thumbs this way. Yeah, I guess. Oh man, it don't look right at all, but I don't know if it's just this is just really weird looking. I don't know which is back and which is forward. That's why that just looks awful. So this is back, and then the down is back. So this is back. So these should be a dotted line. So there you go. And then so this is forward. So this is yeah, it just gets a little confused. This one's forward, so you got forward. Yeah, thumb into it, and then this one is that direction. But that really doesn't get. That's just kind of more practice doing free body diagrams. But what they're saying is, hey, you have an element just like right here on it, and now what? And so I think we can do that. I think what we can do is say that, hey, let's just come over to here to this free body diagram and say, hey, let's say our chunk is right there, and this force is what we're going to see on this side of that chunk. And because you know, you're going to have a chunk over here too. You know what I mean? So this has two forces, but I mean, if we just take the chunk right there, we're going to see that we just have one force. Okay, and in the end, we're going to call this V. F is going to be V, so let's start doing that. So let's go over to our chunk over here, put that same square in, and now we have on the right-hand side an upward force, V. Cool. So now we're going to go back to our chunk, and we've identified, using free body diagrams, I think good enough for me. You know, I learned a lot through this process. I don't think I made any glaring errors. I think my methodology is sound, and I can continue using this methodology. But I mean, they're just looking at this chunk, not the wholeness of the whole object. You know, they're not taking a full slice. They're actually just taking a little chunk out of it, and they want to know. So the force on this side is the only portion that they're witnessing. So like on this little thing, hey, we're now just like isolating this chunk. You know, and now we're saying this chunk, but this force is part of that chunk. Cool, and it's on that side. So there you go. So once we've identified that this force is on this side of the chunk, hey, on this side of the chunk, you must have an equal and opposite force. You know what I mean? Because if we're taking this chunk and then doing that rule like, hey, it's just like the bolt in outer space, you have to have equal and opposite forces. Cool. And then you go right to well, if it looks like it's spinning now in the positive direction, thumbs up, it's spinning. You know, put your fingers in the direction of the force. So now we would need to go thumbs down, and now you would have these forces balancing that torque, and that's what you get. So essentially, that goes to hey, you have a force here, and then a force here, and then a force here. And these forces are acting on the surface of this chunk. So this chunk is a three-dimensional object. Now, this video isn't going to help you learn that, but it's just that we've identified, again, that there's no squishing this way. There's no, like when you twist this, there's no squishing of this, you know, little thing. And so in that direction, nothing happens. And in this direction, it's not getting squished toward the center. You know what I mean? this thing's not going from a cylinder that looks like this to a cylinder that is like, you know, it is shrunken this way and this way. You know what I mean? There's no shrinking in any of those two directions. So this direction, you know, aren't affected by those. But these directions, hell yeah, you're gonna have a force on that face, a force on that face. All right, let's take a little break. All right, hell yeah, got a new battery, and for sure. So now we're able to tackle this square, and we've identified using the free body diagrams that if we tackle that, we're gonna have this downward force, we're going to call it V, and upward force there, call it V. And again, using the sum of the moments has to equal 0. You know what I mean? Just by, you know, if you have thumb in the direction upward, force going that way, so you have a positive moment, so it's got to be a negative moment, and you're going to go V there, V there. Now, this is a free body diagram. This isn't. This is a shear This is a diagram showing shear stresses. So these shear stresses are, and this should be, well, I mean, they're taking out this element, and that's smart. I guess in this case, the area has to be fairly thin, because if you have any element with thickness, well, if you get closer to the radius, you can't take as much force. So like your force that you're going to see on the outside is going to be your largest, and then the inside it can't take any force. You know what I mean? And so you have nothing. Yeah. So yeah, all your strength is happening on the outside of this, and this is where your highest stresses are. This is the strength of it. The inside, it doesn't feel much at all. You know what I mean? The exact middle feels nothing. It's like, what's going on? And the outside is just like trying to hold this whole thing together because you're twisting it like that. The outside skin, you know what I mean? Just like when you're doing this on your skin and stuff, that outside shell or skin is what's holding it back. So that's why they used a very thin slice of area here. We're still going to call it just an area of 1 square inch, or just an area of 1, and because then it can make it easier, because now we have identified that you have a force, and we're saying that the area is equal to 1. Therefore, the shear stress, which is the same thing as like when you're just pulling on a bolt, this direction, force times area. What did we say? We said that stress is in PSI, so use the units to your advantage. This is pounds per inches squared. That means that we're going to have V, your force divided by area. That's for that equation. And then just think this shear stress is the same units, it's PSI, same units as your tensile stress. That's what this lowercase omega is. And so it's going to be the same. It's just that your area is perpendicular. You know what I mean? Your force is perpendicular to the direction. If the area is facing this direction, your force, your V, is going to be in that direction. And that's what we have. So we have V divided by A. In this case, we're just going to say A is 1 square inch. And then so in this case, I just like to make this simple and just say your shear is equal to, or your shear stress, because that's what this is. This is shear stress is just equal to your shear. Oh, and just another S. You know what I mean? Because you would never say, like when you the tensile strength when you put a force on a bolt. I don't know. They call it like the nominal force. I forget what they call it. They don't call it the shear force. They just call it like the force, or like you're pulling on a bolt, maybe in the nominal direction. But the fact that they would use another S word, one being this, shear stress, and the other being shear as the force, that's the nightmare. So we've almost, the only thing this video is not going to cover is strain, that S word, but that is just think change in length. You know what I mean? That when you put force on a bolt, it does actually change in length, very small, but there you go. There's your change in length, and your change in length divided by the total length is what they call strain. You know what I mean? And that's epsilon. But just it's such a brutal subject because you have like 4 things that have an S word, and I would say that shear stress and shear force, man, that's a bummer that those basically are the same verbiage. And I'm equating them right now, but no, that's just because the area involved, I'm just making up an imaginary area that's an area of 1. But there you go. So that's how this free body diagram with your V that way, that way, that way, and that way can be identical to this shear stress diagram where you have a down and up, and then the top one goes to the right, this one goes to that way. And again, you use your fingers in the directions, there you go, and the top ones and the bottom ones go that way. So they balanced out. So both these visually are not moving. You know, if they're just floating in space, it ain't going to move. And that's what we observe here. This thing has no motion, but it's going to rip apart. That is kind of what we're observing. All right, hell yeah. So we did that. Now, we're gonna dive into 2 things. And I'm going to pick the direction I want to go. One is that I think I need to blow this up, so I might take a little break. But it's saying, hey, if you do have a little element and you're putting force on it this way, look, the resultant of these 2 V's is that direction. That's going to be your resultant force. Let's call it R, and your resultant force this way is going to be R. Well, and you're going to get a resultant force that way, squeezing it in and squeezing it in. You know what I mean? So you're going to have 2 components this direction and then 2 components that direction. So basically this little element is going to lengthen and then squash in. And then so I think that is the first thing to talk about when we're talking about pure shear, because this is important, and it's what, it literally is what rips apart, that rips apart chalk, but only because chalk can't take tension. Because what we're showing here is that if you take this little square, put pure shear on it, and like twist it, like you're twisting, I guess we can just go to this piece of chalk, you're twisting this piece of chalk, that you end up getting these resultants, you know, at a 45 this way and a 40. So if we take a chunk this way out of this, if this was a chunk that we took out, and then we even take a smaller chunk and put it at a 45, well, what do we get? We get this, and we're lengthening it this way, and then we're squashing it in that way and that way, and that this is actually brutal. One, you're pulling it apart. Cool. Chalk can't take tension. It's going to rip apart, and it's going to rip apart right on this 45 degrees. But also, you know, materials, if you squeeze them and pull them, because if you just pull on a material, it's going to get thinner. But then if you actually squeeze the material together, it's going to push itself out. And one of the properties of steel is, one, yeah, you can only put so much force on it. You know, if you have an area, PSI, we get that. But the other element of steel is if you have a chunk of steel and you pull it past a certain amount, like let's say you just don't have a scale and you don't know what you're just really strong, and you just don't know your own strength, and then you see, and then it starts to move. You know, at a certain point, and it is kind of microscopic because it's like it's a fraction of, it's 3, if you have a 1 foot chunk of steel and you move it and you lengthen it more than 3 playing cards, well, now that's as much as you've already, yeah, that's as far as you can move it, and it's starting to break on you. You know, it's going to go plastic and break. So the change in lengths are very small when you're working with you know, strong materials like steel. You know, rubber, on the other hand, hell yeah, rubber you can stretch it 8 times this length. Like a rubber band, take a rubber band, stretch it 8 times its length, and then it'll break. All right, hell yeah. So, but that is going to be for another video, because you just get into, I mean, basically what's happening here is that these 2 points are getting farther apart, and once they lengthen, and that introduces that strain element. Well, what the hell did I say? Well, the strain of steel is 0.002. That's such a crappy number because you're just like, it's too small for me to handle, but that's 0.2%. That's where we go, hey, 12 inches. If we take 12 inches and then multiply it by what's 2%? What's 0.2% of 12 inches? Well, no one knows. But you basically have to multiply it by this number, 0.002, and 12 times 0.002, that's 0.024. And what we know about playing cards, and then what we know about so this is 2.4 thousandths of an inch. Thousandths. No, hundredths? No, tenths, hundred. No, this is just 2.4 hundredths. So this is 24 thousandths. But what we know about playing cards is if you have a pack of them, they're a ½ inch. I love this little thing. I go through it all the time. And if you had 2 packs, that's going to be 1 inch. Well, how many cards are in 2 packs? Basically 100 cards. Okay, so if you had 100 cards in a 1 inch, if you had 1,000 cards in 1 inch, well, each card would be 1,000th of an inch. But you just have 100 cards in an inch, so each card is going to be 1/100th of an inch. And if you have a 12-inch chunk of steel, you can move it 2.4 hundredths of an inch. So in between 2 to 3 playing cards, brand new playing cards, is how much you can stretch a 12-inch, rod of steel before it yields, before it starts to go to Play-Doh and people lost their jobs. You know what I mean? So anyway, so that's what's happening here. You have this diagonal. Well, when you're putting that shear on it, it's lengthening, and this change in length can only be 0.002%. And yada yada yada. You get a nice little relationship. And this is literally why chalk will shear apart. If something is not brittle, like if you do have steel in a rod, well, no, it just might melt. It'll turn to Play-Doh and kind of do the whole Dairy Queen, and that's how it's going to break. But if you have chalk can't take any tension. Concrete can't take any tension. If you have a cylinder of concrete and start to twist it, it is crazy because every little square is getting ripped apart at a 45-degree angle, and that part is lengthening. There's 2 ways that you can break steel, is by putting a force that's too much for it, or by just like physically lengthening it past, those 2 to 3 playing cards per every foot of steel. I think you get it. So those 2 things are happening here. You're getting a force at a 45, which is lengthening that chunk, because your forces, these are shear forces, but they're acting on those areas. Like I said, you get a V, 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 V. You get a resultant here, and you also get resultant squashing those in. That double whammy really makes stuff that's brittle rip apart at this helical 45. All right, but that actually is not where we're going to take the end of this video. Where we're going to take the end of this video is, hey, we've observed this chunk, so now we have to, we've observed this chunk that it does have these shear forces, yeah, did I say that right? Shear stresses. They're acting on areas. You could put the areas in, and you could do a free body diagram. This is a shear force diagram. But now what we want to do is be like, hey, we can actually cut this at an angle, and now we want to know how the hell that would make sense at all, and then what's the results that we're going to see. Because it's the same. It's the more complicated step of just saying, hey, if I put a force here and a force here on these faces, obviously I'm going to be tensioning this diamond shape this way and then compressing this diamond shape this way. So if I do have an element at a 45, I'm seeing nothing but tensile this way and compression this way. But let's say you're not at a, this is only at a 45. Let's say you orient your element like at a 10-degree angle. And that's what they're getting at here. They're saying, hey, this angle can be anything from 0 to 90. And that's what we're going to kind of end this video and kind of show that. All right, here we go. And I think we can, I kind of want to do another free body diagram. So if we have that circular chunk that has a, that same torque on it, twisting it, and we do take, and we basically want to take just that element, I think we can actually come in here and maybe, hey, take that little postcard of an element, but now let's kind of connect it to the rest of this cylinder, because here we're saying that we have a force downward and then a force upward, and right here, I guess that's not how you would do it. I guess you would have to take this postcard of a thing and then just hook it into this force. But essentially, you're going to get, it's connected to this force down, which is connected to that force up. So nope, that didn't do it. Oh, I drew these wrong anyway. So if the torque's going in, this force has to go down, and this has got to go up. And, so yeah, and then if we take it there, this force has got to be up, this force has got to be down. So that did work. As long as I drew the line just on this side, because that's all we're focusing on is like, hey, just one side of this, not both sides. Okay, so, but once I do that, and let's go from the other side. So I'm going to come down, get that little post-it thing, and this way, we're going to go down and then up. So force down, force up, and we're going to take our little slice just right there. So now we're going to draw that little thing in, post it, and then we have the, I guess we just do it. So now we're just going to isolate the postage stamp right there on this cylinder, and we're going to say, holy Toledo. Oh yeah, no, we're chill. We're chill. Yep, so this side's got to be up. So we're going to have a force up because the on it is going to be a force down. Okay, so we got that. And we know that you have to put these forces in. And I can do that right away because these two are in positive and then these two are in the negative. Cool, so now I have 4 forces. I observe that it's not moving. There's no rotation. It's not moving to the right. It's not moving up. All the forces are balanced. Perfect. And this is a free body diagram. Free body diagram. Hell yeah. Alright, so I guess what I was getting at is, let's say you take your little postage stamp, but now I want to do like a steep angle. So instead of a square, I'm going to come in here at a steep angle, and then so basically what's hanging on is just that much. Now, is this going to make sense at all? I think it might. I mean, because if this face is the same, and because you have two things here. You have let's say you do have your square, your steep angle. This part is connected to the other side. I mean, so I could have taken. Oh no, yeah, this is interesting. This is interesting because one, I can take the free body. I can cut this. Or this square out on both sides and at least find that this face has a downward force, this face has an upward force. Like, I know I can do that. But in this case, I said, hey, I'm going to take a slice that looks like that. Well, this face is a full face, so it's got a force on it. But now, but now we have an angle here. So this can only take a, and let's just do it first like a 45. You know what I mean? So we have this downward force, and now, and we have a full face here. These two faces are the same, so we know that that face is going to be a full F force. And now we have a normal force, and we have a shear force. And I don't even know how to draw them in, but actually the shear force, if it's a 45, is nonsensical, because this is a free body diagram. These two forces, their resultant is going to go that way, which matches the normal force. So at a 45-degree angle, you're only going to see a normal force and no shear force. So that is the first element that we're going to go over. Is I think it's, so this is a free body diagram. It's saying, hey, I took the shear stresses multiplied by the areas and got the force. And so what's happening here is we're saying that, hey, all four sides of this has an area of 1. So keep that in mind. You know, just area of 1, area of 100%. But then when we would go to make our slices at this angle, and just know that we can make it at a steep angle where this area is still 1, and this length is small. You know what I mean? So we have a small length there, but this length is greater than 1. You know what I mean? So if we do have a 45, this is 1, this is 1, this is the square root of 2, or 1.414. So yeah, keep that in mind. Because now if we do have a shear on that area of 1.4, that gives us the force. So the force along this shear plane is going to be the shear that we're going to try to figure out how much shear is on that face times the area. Shear times the area is force. So force is PSI, pounds per square inch, times inches squared. Force is shear times the area. You know what I mean? And I think it's easiest to go back to that, tensile stress. Tensile stress being in PSI is equal to force divided by area. And then therefore force is equal to tensile strength times area. But that's where you get this. Force is equal to shear times area. Now right here, area is, the area of 1 is equal to A naught. So they're just calling it A naught. I just like to call it 1 because, hey, it's going to be that there's a percentage of the area in all these. So this is just 1. So your force is just equal. So tau is just equal to V. So this I would call V. This would be V tan theta. So your force is V tan theta. This is V secant theta. Now we got to talk about secant, because secant theta is just equal to 1 over cosine theta, and that's maddening because I haven't even memorized that cosecant theta. It's related to sine theta, and secant theta is related to cosine theta. I think that's kind of the hardest thing for me to memorize because I'm hardly ever never using cosecant. But secant comes up occasionally, and it comes up in this. But just know that these are just, cosecant theta is just 1 divided by sine theta. All right, hell yeah. So now we're involving a little bit of trigonometry, but we still got to keep focused on the free body diagrams and how they're related to these shear stress, or stress diagrams, because this has tensile stress. This is your tensile, and this is your shear. And hopefully that's what they call it, tensile stress. Nominal stress, tensile stress, shear stress. Plane stress? Do they call that plane stress? I don't know. I'm sure there's, but that's your basic. And your shear is kind of what we're learning. Cool. And at a 45-degree angle, we found that there was no shear stress because you can just look at the free body diagram. Hey, you have two forces going that direction, resultant this way, has to be balanced with that going that way. And then your shear is in the middle. So let's just show you the kind of the, so here is the chart. Here's the graph for this. So, and this is good. And we got to put some sort of end to this video. So what we're going to do, and slow down. I didn't like this drawing because it's at a 45-degree angle, and they're saying that theta is arbitrary. So the first thing that I did was be like, hey, let's draw just a real steep angle. Okay, so we know that this area did not change, and we know that the shear stress, so we know that the shear stress on this face and this face never change. But the second we slice into it, this shear stress can change. At a 45, there is no shear stress. They're literally, if you cut at a 45, it doesn't feel anything. And don't confuse that when I was talking about the bowling ball on sand, because that was in pure compression, and hell yeah, at a 45-degree angle. It felt 70% of it. So what we're talking about is this special case of just pure shear. When you're taking something and purely shearing it, well, one, you wouldn't think that there is nominal or tensile stress, but at this 45-degree angle, you can very obviously see that you're taking this little square and then just ripping it, pulling it at a 45, and then squashing it in perpendicular to that 45. And so that gives you a tensile stress along that 45 and a compressive stress perpendicular. But what you don't have is a shear stress along those molecules oriented at 45. So that's where this chart says, hey, at a 45, this shear stress goes to 0, and you just have tensile stress. Oh, they're calling it normal. You have normal stress. Normal stress versus shear stress. And that's crazy because you have a word, I don't know. That's why the word shear has shear stress and shear. This is a shear force. So this force is V. This is your normal force, is N. So you have a normal force and this is your normal stress. But you could also say this is a tensile stress, and then this is always a shear stress. So that's where the verbiage I do not like. But because these are forces, this is your free body diagram. This is a stress diagram. Okay, so these are not additive. If you take this number and this number, and then if you sum the numbers in the x and y directions, they're not going to equal because they're a function of the surface area that they act on. So this normal at a 45, this normal stress acts on this area, which is 1.41. It's the square root of 2. And how we know that is because we're just saying, hey, this area is 1, this area is... Well, we're saying that this area is 1, and because the angle is a 45, that means this area is 1. 1 squared plus 1... Alright, hell yeah, my computer is overheating, so yeah, let's finish this. Alright, so we have this element. Again, all areas are the same. At a 45, you have this area is 1, this area is 2. So this area must be 1 squared plus 1 squared square root of that. This is the square root of 2. So there you go. And now you can find the force in this direction. The force in this direction is just going to be this shear stress times, and then this should be 1.41. So now we're going to, I think we should, well, maybe we'll get to that later. So what we were doing is like, hey, we're going to take a really small slice. This area is still 1, and we're gonna call this V. You know what I mean? So we have a downward V, which is just our normal shear, or just the shear stress on that unit area, and we're calling that V. And or maybe we don't even need to do that. But heck yeah. So this this arrow is going to represent the magnitude of that downward force. Cool. And if we have a small area, well, we have the same shear stress, but it's just over a very small area. So this force is going to be a smaller arrow. And if we do that, now we have, again, we can be like, hey, this thing is just floating in outer space. I just put a huge force on it downward, so this thing should be moving downward. But what we're observing is that these things are static. There is no motion. So, and then we cut away this face, and again, we can do two things on this. And I'm just going to do in arrows. We can have a force in this direction, a V, a shear force, or we can have a normal force N. And if we look at this shear force has to be counteracting this force. So this one is going to be a big arrow. And once we do that, okay, these forces, the forces kind of in the y direction, are equal now. But we have this going this way. We know that this is going that way, and then we know there's a component of this going that way. So we do have to have some sort of normal force to counteract it, but this is going to be much smaller. So now what we're going to do is we're going to even take a thinner slice, like almost a 1 degree slice. So this is going to be your full magnitude. This, we're just going to say, is equal to 0. It's non-existent. And then this is literally kind of just in the same direction. So we're going to say that these are equal. So these are equal. And then the normal direction, which is basically perpendicular, would counteract this, and then maybe a real smidge of this, but hardly anything at all. So we're going to say that normal force is 0. So there you go. Normal force is 0, and then this shear force has to equal this force. And if we're calling this V, so we can do either way. You know what I mean? So we can say that there is a shear stress. Never mind. This is a free body diagram. You know what I mean? That's what we kind of want. We want to go right to the free body diagram and say, hey, no, this is a real force. This is a real force V. We don't have any force going this direction, and then this force is basically V. And then our angle is like a 1 degree angle. And then our normal force is basically 0. Okay, cool. And then we can take the area. So if this is only a 1 degree area, what's the area of this face? The area of this face over here is 1. We're going to call that area of 1. But with just a 1 degree slice, the area of this is basically approximately 1, 2. So now we know that this face has an area of 1. We know that it has a force equal to V. And now we can find the shear stress, because the definition of shear stress is force divided by area. That's going to be V over 1 is V. So tau is equal to V. So, and that's what we see. We come over here to our chart. If we have an angle of 0, our shear stress is maximum. Our shear stress is just equal to, or this tau naught. This tau naught is equal to tau because the areas are the same. When you have 0 degrees, the areas are both the same. So now let's go to tau at 45. And then what this shows is it actually shows what direction the shear force is in. So we know that if we cut it at this angle, our shear is up and our normal force is away. This diagram, what they say is like, hey, they're just guessing. That they're just putting this shear force in a positive shear. So what a positive shear is using the right-hand rule, my thumb should be up out of the page or counterclockwise direction. So they're putting in this force or this shear stress that generates a force in that direction, and they're calling that positive. Now, even on our graph, if we throw in an angle of 60 degrees, well, look at that. Our shear stress becomes negative. So maybe we should solve, kind of that one next. if we throw a shear stress between 45 and 90, if we throw this angle between 45 and 90, our tau of 0 goes the opposite way. So let's just do free body diagrams and show that. So what I'm going to do is I'm going to keep this element the same, but now I'm going to do like a real steep angle. So I mean we're talking like way out there. Okay, so now we have this. Now we're going to do a free body diagram. We're going to say that, hey, we've identified that this face has that T, and that's our shear stress, and it's an area, and our area is 1. So now we're going to say, hey, we have a downward force V, and that now we're going to make, and we know that this bottom edge has that same shear stress, but the area is much larger, so that force has to look like that. You know, now you just have a bigger force. And I guess we don't even need to label these. We're just doing a free body diagram, and we're just kind of showing the magnitude of the forces. All right, hell yeah. So now, and again, those are the two we do know. The two we don't know are in this normal direction and then in this shear direction. I'm not even going to draw arrows on them because we just don't know yet. But like I said, we're observing that this thing has no motion. You know, it's not moving to the left, to the right, up and down. It's not spinning. So, hey, look at this big force to the left. We must need to counteract that with a really big force to the right. You know what I mean? Because if in this normal direction, we could counteract it with this normal direction because it's got a component going that direction. See how if we do like a big one, hey, we do have a small component, but that small component would never equal this force. So heck yeah. So we have, and this is our shear. So we have a huge shear going that way to counteract this. And this is going down now. So we do have a component of this going down. This is going down. And so we do have a normal force going up. So there you go. So we have a normal force and then the shear force. Now let's take this to the extreme, just like we did the other example, and say, hey, let's say we hardly have any. Now this angle right here is what we're interested in. This is almost 90. It's like 98 degrees. Now, this is going to be shrunk down because I'm going to still say that this area right there is 1. So, like this could be scaled down also, you know, just to be like, well, there. But we're still calling this area of 1. You don't need to. You could call this area 7. I mean, if this area is 1, this area is 7 for sure. If this area is 1, there's like 1, 2, 3, 4, 5, 6, 7. But you could also say that inverse 7 inverse, you could also say that this area is 0.142 and this area is 1. You know, it doesn't really matter. I'm just using the idea that this A naught is kind of like my representative of 1. But anyway, so this area is 1 and this area is like huge, you know what I mean? So we're going to have a downward force, but now this force downward is just almost 0. It's like potatoes compared to this force to the left. This dominates, so we have to, and then we can only do a shear and a normal force because we cut this at a plane. So what we're doing, we're taking our square element and we're cutting it, and once we cut it, we can only, you know, hold that thing together by a shear and a normal force. Okay, so this shear force in this direction, and then there is no normal. So at 90, we have 0 normal force, but our shear force is in the negative direction. And how do we know it's in the negative? Well, you sweep our fingers in the direction of the shear, our thumb goes into the page. So this is in the negative direction. So what they'll do is just be like, well, I'm just going to draw at whatever angle, even though they're saying the angle is real steep, almost like 90 degrees. And they're just showing that this force, or this tau of 0 is up. But in essence, in this case, if we drew tau of 0 or tau of theta up, this would be a negative T, negative shear. And that's what you get. Okay, holy Toledo. It's getting late, and that's kind of what I want to go over. I mean, we really covered free body diagrams, and this was cool because like the second you get something like this and you're like, I don't know what direction that goes. Like these, I do know. I have this square, I got all 4 of those. It took a lot of tutorial just even to get to that much. And now we cut on a slice, and what they do in the book is just say, hey, just take your normal force as always being in the tensile direction. That's the positive, even if it was compressive, because we could do that. I mean, ultimately they were saying if you cut it at a 45 that way you'll get a compressive. So let's do that and see if we're able to. So we're gonna go. Here's our chunk. And now we're going to cut it at a 45 this way. So now we're going to take this chunk. All right, let's see if this works. So now we have a force that way, a force that way. Oh, look at this. Look at this. It is working. It is working. Because now we're going to put the... So these are the forces we do know. Right there. See how this force is down? We have a V there and a V there. I don't know. You can label them whatever. But then over here, you know, by sign convention, you're going to put your shear in a positive direction. And if it turns out negative, this is a free body diagram. If it turns out negative, cool. You know it's negative. But now we're going to put our... well, and then let's not. You know what I mean? So this is the only one we don't know. But just from symmetry, like I should just get rid of this. These are the forces that are acting on those 2 faces. And these forces have to be resisted. And again, this thing is not moving. They have to be resisted by a combination of forces in this direction and then this direction. Well, these 2 are perfectly symmetric going that way. So this direction, your force, your shear force is 0 that direction. That's why I didn't want to call these V. These are just forces. There you go. And they're equal. That's why you don't have any shear force. But look at this. The resultant of these are going that way. That's the resultant. So you need to have a force, a normal force that way. So there is your normal force, and it's in the negative direction or compressive direction. So there you go. And that is kind of the bread and butter of like how you take a square and you're like, well, how the hell did they even get these faces? Well, cut this up, you know what I mean? To get this face, you would take this square, cut along a 45, and then you have to take this. So now let's do that. You know what I mean? You know your 2 forces. I mean these areas at a 45 didn't change. So this is going to be an upward force that direction, and this force is equal to tau A naught, or when we're just calling A naught 1. You know what I mean? So it's just your force is equal to tau. This direction, your force is equal to tau times 1. You know what I mean? It's a multiple, tau times 1. You probably should do this just so you know that it is a force. It's not a pressure. But there you go. And now you have to have, because you cut this, you have to have a normal force and a shear force to kind of hold this motion. I mean, again, this thing cannot move, and you just put a resultant. These 2 forces add to a resultant that way. So obviously you're going to have a force this way, a normal force, but you're going to have no shear force if it's at a 45. There you go. So that's how you would get that face. We already did this face. To get this lower face, same thing. You know what I mean? Take your square, chop it at a 45. You got to take that. And so then you just do the same thing. You have a force that way, a force that way. These have to balance. The only way you can balance them is with a shear and a normal. Your resultant is that way on those, so you have to have a resisting force that way, and then just your V is 0. You know, no shear force that way, just a normal force. And that's what you see. You have a normal force going that way. There you go. There you go. And how they get this, I mean, let's do that, because we're going to say, hey, this is tau times 1. This force is tau times 1, because it's the shear stress is acting on the area, and we're going to call that area A naught. A naught is 1, you know what I mean, just in general, because we want to know, because, hey, this area is much bigger. If this area is 1, this area is 1, this area is the square root of 2, or 1.41. But, check this out. Only the components in this direction, like, so the components, so this force has a component that way and that way. This component has a force that way and that way. These two components just cancel each other out. Cool. So if we take the forces in this direction, we're only going to have, and this is a 45, and the sine of 45 or the cosine of 4, it doesn't really matter, but is 0.707 or 70.7%. So now you have, of this, you only have 0.707 tau going up plus 0.707 tau going up. So these two, the resultant of these two forces, and then just know this is the square root of 2 over 2. Square root of 2 over 2 is 0.707. So if you add those two together, you get the square root of 2 tau. So your resultant is the square root of 2 tau, or 1.414 tau. Cool. So now you have a force, a normal force, that is equal to 1.414 tau. That's the force. But now you want to know what this is, the normal stress. Well, the normal stress on this face, you know, because that's the particles. How much psi every particle on that face is feeling. Well, we need to do our equation. Stress in psi is equal to force over area. So if we're trying to find the stress, we need to take that force, which is 1.414 tau, and then divide it by the area. Well, we know the area, so it's kind of like, you know, it cancels out. 4.414 tau divided by area of 4.414. Those cancel. Now we're just left with tau. That is why the normal stress, and stress is just the psi on all these molecules, is going to be equal to the same shear stress that we initially identified over here. And we identified this shear stress by maybe finding the force and the area that we're taking it over to. Anyway, cool. So we did that, and I think we're about done. All right, hell yeah. Hell yeah. You know, the only other thing is that we can really lay into before my battery just overheats is why these are secants. You know what I mean? We should talk about that, because kind of the rule of trigonometry that you should always just put in your head. Anytime you're dealing with sine and cosines, those are just numbers between 0 and 1. You know what I mean? Cool. And my brother's like, well, -1 to 1. -1 to 0 to 1. And it's like, hey, that's true too. That's true too. Because they oscillate between 1 and -1. But in essence, I'd like to think of them as a percentage between 0 and 100%. You know what I mean? You're really not getting out of that. But the other ones, some of the trigonomic functions definitely get large and get, you know, go from 0 to infinity. And that's going to be your tangents. That's going to be your, and your secants. Because, okay, so this is cool. So if your sines and cosines are numbers between 0 and 1, and cosecants and secants are 1 divided by numbers between 0 and 1, well, you're either going to get 1 or you're going to get infinity. So cosecants to secants are numbers between 1 and infinity. Cool, we got that. So then the other little rule for tangent theta, you should always just write as sine theta divided by cosine theta. And sine and cosine are numbers between 0 and 1. So this could be 0. Cool. So all numbers are 0. 0 to 1, all numbers are 0. Or this could be 1, and this could be 0. So then 1, this could be... So you're going to have numbers between 0 to infinity. So tangent, you're going to have numbers between 0 to infinity. And cosecant, secant, you're going to have numbers between... this you're going to have numbers between 0 and infinity, but cosecant and secant, you're going to have numbers between 1 and infinity. So it is a little bit different. It is a little bit different. And that's cool. This is so cool because and I mean, with these little cheats or shortcuts to have in your mind. I mean, you can do visual things with trigonometry because you're just like, what are you talking about? Well, let's do this one. Cosecant secant is numbers between 0 to infinity. Well, I mean 1 to infinity. Yeah, 1 to infinity compared to 0 to infinity. I mean, those two are different. You know what I mean? One starts at 1 and goes to infinity. The other starts at 0 and goes to infinity. And then so this is the one that starts at 0 and goes to infinity. And this is the one that goes from 1 to infinity. So what gives here? Well, if you have... So I always start with angles of like 0. So you have this triangle, and there's your angle. And then let's start with an angle of 0. Well, this face is 1, and this face is 1. Well, didn't we say we started at 1? Yeah, secants and cosecants start at 1. But then if we take it all the way out to an angle of 90, well, look at this. You know, this is scaled up, but this is still 1, and this is your infinity. You know what I mean? This is just... And this angle is 90. So there you go. So now this face right there is infinity. Cool. So now let's look at this tangent one. And I shouldn't have put this infinity on it. This is the top face. This is the hypotenuse we're talking about. Now this thing, if we have a 0 degree angle, well, this face right here can start at 0. So that's why we go over here. Because sines and cosines can go from 0 to 1, 0 to 1. So you have 0 over, yeah, so anyway, we already talked about it. We can't repeat ourselves. But anyway, so hell yeah. So when you have an angle of 0, you're going to have nothing there. You're going to have no face there. But then when you have an angle of 90, well, hell yeah, it's going to go to infinity. Same thing, infinity, infinity. So now I can draw this infinity back in. Both these are infinity. And we learned something about sines and cosines. Okay, I'm not printing this over again, but we need to know that secant is just 1 divided by cosine theta. There you go. And we need to figure out why that works. Because if I just gave you this triangle and said, hey, this area is 1, and when I sweep it out, I want to know what this area is. Or I'm basically saying length. Let's say I say this length is 1, but we know this is 3-dimensional because the shear stress has to act on an area. You know what I mean? So you do have that. That goes back to, well, can't get too deep. And I don't have that sheet of paper anyway. Oh, that's a bummer. I wonder where that one went. Anyway, yeah, that little slice. I don't know where it went. Anyway, got to move on. More time on the clock. Okay, so, and this is kind of complicated for me too, but so what we do need to know is that when this is 45, this has to be the square root of 2, or 1.414. So let's throw it in there. So we're going to say that 1 over cosine 45 is going to be 1 divided by 0.707. And what's the 0.707 inverse? Is 1.414. So that checks out. Because this literally is 1 divided by the square root of 2 divided by 2. Which is 2 divided by the square root of 2. Did I do that right? Yeah, square root of 2 divided by 2, which is 2 divided by the square root of 2. 2 divided by the square root of 2. Square root of 2. Oh, that's bizarre. 2 divided by the square root of 2 is the same thing as the square root of 2. I don't see it. But, okay, cool. Yeah, I mean, that's what it is. But anyway, and then this tangent one. So at 45 degrees, you basically have, this has to be 1, and that's going to be sine of 45 divided by cosine 45. Well, those are the only time that sine and cosine are only the same at 45, so then you have 1 over 1, so that's your tangent. And then everything in between, you know what I mean? Because if you only have like 30 degrees, you're going to have sine 30, which is 0.5, divided by 0.886, which is 0.5 divided by 0.886, so that's going to be 0.56. So at 30 degrees, it's almost halves, you know what I mean? So there you go. And that's what we know about 30-degree angles. 30-degree angles, if your hypotenuse is 1, this is 0.5 and this is 0.886. So that's why at 30 degrees, it's 0.5566. Anyway, so those two, and then the way to find the secant, I wish I had just some. I'll throw some more paper in here. But yeah, I think you do need to. So if you have theta and you know this, so that's the thing. This problem comes down to, hey, this is the only face you know, and we're calling it A naught. A naught, or call it 1. You know, I like to call it 1, but you can call it A naught. So now if we only know this, we need to find the length of this. And the relationships that we have are that this is the hypotenuse, and this is the angle. This is this, I call this the sun shining on the sinin part. So this part would be your sine theta part. This part would be your cosine theta part. And that's just how I remember it. And your cosine theta part relates this adjacent divided by the hypotenuse. And your adjacent and your sine and your adjacent are always smaller than your hypotenuse, just by geometry. You can never have your adjacent bigger than your hypotenuse because it can be equal. I mean, if the angle is 0, your adjacent can equal your hypotenuse. Cool. Or if the angle is 90, your you know what I mean? Your opposite can equal your hypotenuse. Cool. But we just know that cosine relates adjacent and hypotenuse. And if this is the angle that we have, we want to know the hypotenuse, and all we know is the adjacent. Cool. So now we would say, hey, rearrange this equation. We want to know the hypotenuse is the adjacent divided by cosine theta. But we know what the adjacent is. The adjacent is A naught, or 1. Cool. So our hypotenuse is equal to 1 divided by cosine theta. That's all they had to do. You know what I mean? That is all they had to, and even for me, it's like I should be able to spit that out, but you know, that takes a little time for me. But I do always say, hey, find your angle, say that the sun is shining on the sinin component. That means this other component is the adjacent component. And the main relationship is your hypotenuse is always bigger. Hypotenuse times cosine theta is your percent of your hypotenuse in the adjacent direction. You know, this is your percent of the hypotenuse in the adjacent direction. So there you go. So your cosine is going to be kind of like a percentage between 0 to 100% in this case. That's why I say sines and cosines are between 0 and 1, because I'm always looking at a three-dimensional object that doesn't have negative length. You know what I mean? But you can kind of sweep it this way and be like, hey, this is the positive x direction. So if you take your angle and go negative with it, this is going to be your negative x direction. Anyway, all right. But hell yeah, so that's how that's how this length is related. It's a 1 over cosine theta, and that 1 over cosine theta is just secant theta. So they could have written this area, instead of A naught secant theta, they could have just said A naught divided by cosine theta, which is exactly what this is. This is A naught divided by cosine theta. I think that would have been just simpler. I just don't know why you need in textbooks to make everything just at the verge of insanity, where you just have to have a PhD in trigonometry instead of just, hey, use something we know. If all you have to do is divide it, that'd be way easier. You know, even if you did A naught cosine theta to the negative 1, I mean, for the love of God, anything would be better than throwing the secant in there. Tangent, you know what I mean? We can handle that. All right, so, but that does it. I guess I really want to end this video, but we might take a look at that one. Oh yeah, there it is. See how this has area? So this shear stress is related to the area on this, and shear stress times area is equal to that shear force. There you go. And then you can just do it in units. PSI times inches, you know, pounds per inch squared times inches squared. Those cancel and you get pounds. All right, so now that we talked about the cosecant secant business, I think we can lay into this last part, which is just going over the math of this free body diagram. I said that these do not have to equal. You know what I mean? If you added the shear stress in that in the x directions, these aren't going to equal. But if you take the shear stress and multiply it by the face they act on and get the free body diagram, these are forces. You have a shear force down, shear force to the left, a shear force at that 45 going up. Could be negative, could be positive, you know, depending on the angle of this triangle. In this case, it's a 45. There is no shear force. So it's kind of a weird diagram when it's written like this. Anyway, and then you have a normal force. Cool. So now what we try to do is we try to figure out these two equations. You know what I mean? Hey, I just want to throw in the angle, and then I know that there's a shear stress. I just have one T on this element, and I'm just choosing one angle. So what I want to get is down to this relationship. Say, hey, I throw in the shear stress, throw in my angle, and out pops that number. Out pops that grid that we were talking about. Maybe make it a little bit bigger. Is that, and we already did this. When we took the element to a 45-degree angle, there was no shear stress. Even though we're in perfect shear, at a 45 it's just tensile and compressive stress. And in this case, we're only worried about the angle this way. You would have to cut it, you know, the opposite way to get that negative compression. But that's. All right, hell yeah! I think my camera battery died on that one. Okay, but hell yeah! So what I was talking about is you cut this thing at angles, and you're going to get that shear and that normal force. I mean, but basically, I mean, if you don't have a shear force, if you cut it and from your free body diagram you identify that you don't have a shear force because you're at a 45, well, guess what? You don't have a shear stress. So this equation just kind of solves, you know, it solves the free body diagram, so you can just throw in the angle and then know that the shear stress in the beginning, and it pops it out. Okay, and I guess the lead in here. Oh yeah, and then we said at a 45 you don't have any shear force. You just have normal forces pulling, but you also have the forces this way, but you would have to chop it at a 45-degree angle opposite, you know what I mean? So you would have to chop it at an angle of let's see, I mean, you would have to get an angle like this, and then the piece would be over there. So if this was your original theta, whoops, kind of spitting, you would have to go all the way to there, you know what I mean? So there you go. So 360 minus 45, so it would be a 315 degrees. That's one way to look at it. And let's throw it in. So we're going to go 315 times 2, that's our angle. We got to get into degrees. And we're going to go sine of 630. And we get -1. So there you go. So it does work, you know what I mean? That was a good way to do that. Yep. So that was interesting. Okay, but I think what we want to do is go through the math of how they get sine 2 theta and cosine 2 theta. Now, one is just that like I said, you have these key points where you're just like, okay, when I start out, I have, when theta is 0, I just have pure shear. You know what I mean? If theta is 0, I just have this line, and I have a shear down and a shear up. No normal forces to the side. So that's what we see. When theta is 0, with the angle is 0, just all shear. You know what I mean? Cool, cool. But now at 45, the shear goes to 0. Okay, so what do we know about sine and cosine? Well, like cosine starts at a high, it starts at 1. When cosine of 0 is 1, you get 1. But then when cosine of 90, you get 0. You know what I mean? So, but we're getting for this shear, we're getting at 45 degrees, we're getting 0. So we need to take this 45 and multiply it by 2. So that's basically what's happening. If you take 45 times 2, heck yeah. And then if you take cosine of 45 times 2, that's cosine of 90, you get 0. So this graph is basically just sine of 2 theta. You know what I mean? You throw in 0, you get 0. Throw in 45, you get 0 again. And then so it's just a quicker representation. So here's, the red is cosine x, blue is cosine 2x. Whoa. And I got to get back to radians. Damn. Oh, and it's not going to be very good. But yeah, so there's your red is cosine x, and then the blue oscillates twice as fast. Okay, we can move on. Yeah, I think the trickiest thing is they use secants and tangents. Throw some more time. All right, let's see if we can do this. Kind of the last 5 minutes. Damn. All right, so you have this generic. Oh, we gotta throw in more light. Damn it. All right, even I want to be done, but I think we got it. So what they do in the textbook, like I would just sum in the x and sum in the y. You know what I mean? If you summed in the x, you would have negative tau a naught tangent theta. This doesn't count, and then you would have like, hey, this has a component, and then so, but this is kind of tricky because I would do it at a lower angle. Because now here, this theta is representative of that theta. Okay, I see that. So now that's the theta right there. But then this one, you know what I mean? You have to go up. So that's that theta. Okay, but anyway. So how I would just sum in the x. You know what I mean? So you have negative tau a naught tangent. But we're going to add the component. So if this is the angle, the sun's shining on this vertical part. But we want it in the x. So we want the adjacent. See how you do that real fast? I make other videos on that, but so that's going to be your sigma theta a naught secant theta, but it's in the cosine theta. You know what I mean? So that's how you do that. And again, I'm going to do it one more time. But here is your angle, so this theta is equal to that angle, and we just want the component in the x. So if this is your hypotenuse, which is, I mean, this whole thing is normal, the normal stress, a naught secant theta. But if you multiply by cosine of theta, you get this adjacent part in the x direction. So that's that. Okay, and then I would say, hey, this is the component this way. If this is your angle, this is your sun shining component. So we would go sine theta. So we would go tau theta a naught secant theta sine theta, and that would be negative because it's going in the negative x direction. So minus tau theta a naught secant theta sine theta. Cool, and you would do that, and you would equal that to 0. And then you would do the same thing in the y direction. But what they do instead is say, hey, let's not take the x direction to be that way. Let's take the x direction to be, they're going to, what do they even call them? What directions? They're just going to say, we're just going to take it in the normal stress direction and then the shear stress direction. So that's how they did in the textbook. So they're going to say in the normal stress direction, you're going to have the normal stress A naught secant theta. and then instead of saying minus all the others, because that's the only one in this direction, this one's perpendicular, so that isn't even in this direction at all, but these do have a component in that direction. So that's where now you have to figure out where your angle is, you know what I mean, which is kind of crappy. I mean, but yeah, here's your, on this one, here's your theta, and on this one, your theta is the opposite of that, you know what I mean, because if you have, if this is 30, this is going to be 60, so this is 90 minus theta. And what they use, the trick, like let's say they're trying to find this component based on this 90 minus theta. Well, if this was your angle, this would be your sine component, but because it's 90 minus theta, this is the cosine component of this angle. So that is the other flip-flop trick that they do. See, they're just using too many tricks at once. So they say, hey, you have that sigma theta A naught secant theta minus, but instead of minus, they're just saying it's equal to, they're doing this one first, tau A naught, and then we're trying to get this direction. This is your angle, this is the sun shining, so that's just going to be your sine theta. But now on this one, they're going to go tau A naught tangent theta, but instead of doing, so here's the component that they want. It is in the sine theta direction of 90 minus theta, so if you did sine of 90 minus theta, these are equal. So cosine theta is equal to sine 90 minus theta. So that is the quick trick they did there. Okay, and now they're going to simplify this to here. And let's get more time on the clock, because this is the maddening thing. So now they're just going to resolve it just for the normal stress, sigma theta. And so you're going to have to divide everything by A naught secant theta. All right, so everything is divided by A naught. We can handle that. But now you're going to divide everything by secant theta. So this first term goes from sine theta divided by secant theta. And I think this is where it gets confusing. Secant theta is just 1 divided by cosine theta. So this whole thing becomes sine theta cosine theta. Do you see that? Secant theta is just 1 divided by cosine theta. That's the same thing as secant. See how you flip it up? But yeah, so that's how they get sine theta cosine theta. Now tangent theta cosine theta is also sine theta cosine theta times cosine theta. So now this tangent, oh, and maybe I messed up too, because we're dividing by secant. Secant theta is 1 over cosine. No, I think we're good there. Tangent theta is sine over cosine, and now we're multiplying by sine. Oh, bummer. Yeah, even I'm messing up here, because they're getting tangent theta is sine divided by cosine, and then they're multiplying by cosine. Yep. But ultimately they're getting 2 of these sine cosine terms. So oh, I had it. It's so weird how like you're just like, oh, I had that, but now I'm not getting it. So we're dividing. Oh, no, I'm sorry. I'm sorry. Well, yeah, holy Toledo. We're taking this tan theta cosine theta and dividing it by secant theta. So that's crazy. So now you have to take this tan theta and say that sine theta divided by cosine theta. This cosine is just cosine theta. This secant theta on the bottom is 1 divided by cosine theta. So now with 2 of the cosines cancel, and now you're just left with sine and cosine. So that's where they did there. And now you have the same thing twice. You have tau sine theta cosine theta plus tau sine theta cosine theta, which gives you tau 2 tau sine theta cosine theta. Holy Toledo. Okay, now they're going to, so that was just in this theta direction. Now you're going to do the same thing. Sum all the forces in the tau theta direction, and the easiest one is the first one. Tau theta a naught secant theta. Cool, that's going in that direction, for the love of God. And then you're going to equal it. And I don't like the fact that they equal it right off the bat, because this first term would be minus, which is this, because you have this term, and if here's your angle, here's your sunshine component, this is your adjacent, and that's what we want. And we're trying to find this line, and this is the negative. So yeah, your first component's negative, or just equals to the, so it's this tau a naught cosine of that angle. Cool. Now your other component is going to be tau a naught tangent theta, but it should be cosine of this angle. It should be cosine of 90 minus theta, but they're just saying that's equal to just sine theta. Cool. All right, so we can dig. And then this one, you have to divide by a naught secant. So you're taking this and you're dividing that downstairs. A naughts cancel, but now you have cosine theta divided by 1 over cosine theta. This is going to be cosine squared. Cool. Now you're doing, this is going to, let's see if we can do this in our head. Sine theta divided by cosine theta is tangent, times sine theta, that's going to be sine theta squared divided by cosine. And then you're dividing it by secant theta, which is 1 over cosine theta. So the cosines cancels, and now you're just left with sine theta squared. So you're left with cosine theta squared minus sine theta squared. Now we all know that cosine theta squared plus sine theta squared is equal to 1. But I think it is a good thing to know that, now this is where I learned a new identity. I think you learn enough fundamentals of trigonometry that you add in an identity every year, you kind of learn one more. So this new one that I learned was just like, oh, hell yeah. So if I do have, cosine squared minus sine squared, and in this case, what do I get? In this case, I get the cosine 2 theta. So in this case, and I'm sure sine squared theta minus cosine squared theta is going to be sine 2 theta. I'm probably positive, this cosine component is what you're taking. You're going to minus the sine component, and then hell yeah, you're going to get, in some cases, a positive number, but and equally, you're going to obviously get negative numbers too, because half the time sine is bigger than cosine. But anyway, but this is a good identity. I threw in cosine of 30. Or did I? No. Well, you got to get in degrees. There we go. Cosine 30, which is 0.866. We're going to square that. That goes to 0.75. That is one I knew. So we got 0.75. But then sine 30 is 0.5. Square it is 0.25. So now we have 0.75 minus 0.25. And we get 0.5. What do we know that's 0.5? Well, that sounds like for this case, that sounds like 30 degrees. So sine of 30. But it's going to be a cosine thing, so that's going to be cosine 60. And that's going to make sense because that's going to be cosine of 2 theta. We started with 30. We put a 30. So 2 times 30 is 60. Cosine of 60 is 0.5. So that one definitely checks. And it's just good to do ones that check. You can throw in any number and it's going to work. But there you go. So we got 2 cosine 2 theta for that one. And then over here, I guess the relationship is, hey, if you have 2 sine theta cosine theta, you're going to get sine 2 theta. So we're going to throw in 30 here, because sine of 60 is 0.866. That's what we're trying to shoot for. So we have sine of theta, which is sine of 30 is 0.5. Cosine of 30 is 0.866. Multiply those together, you get 0.433. Multiply by 2, you go back to 0.866. Oh, this identity is really easy, because now we just know that this is, we started with 30, but you know this is going to be sine 60, so it's going to be sine 2 theta. Anyway, so that's how I try to learn trigonometric identities using very simple. I always use like 30 degrees, 45 degrees, 60 degrees. Those are the bread and butter, because I kind of just know those to 3 decimal places, and you can play around with it. Because even if you have like sine 60, that's going to be 0.866. But if you have sine squared 60, sine 60 squared, 0.866 times 0.866 is 0.75. You know what I mean? You get those cool, you know, those are the, I like to work with those anyway, because sometimes you do pop out some simple numbers. Anyway, that was it. That was my kind of attempt at learning shear, and this was good. You know, probably just for me, but hell yeah. I mean, that's all we wanted to learn, is like, what the hell is shear? And the fact that shear, if you shear this way, you're shearing the other way too. I mean, you're putting a shear stress. Yeah, you're tearing it apart locally, kind of in you know, kind of both directions. I think that's fascinating. The reason why if you shear a bolt this way it doesn't just split in two is because your surface area is huge, and only down to a localized little nugget. Yeah, maybe this localized little nugget is actually ripping apart sideways on the top and bottom. But ultimately what you're left with is two halves of the bolt and then a shear plane, and then obviously these small little elements, yeah, you have to draw them really small. You know what I mean? That's the only thing that makes sense. We showed that if you did a big element, you can use it to figure out free body diagrams. And hell yeah. So I'm pretty satisfied with learning free body diagrams. And again, we'll just get better. This was just me trying to do this in under 3 or 4 hours. And you know what I mean? I think we did it. Pen drop. Thanks for joining me. And guess what? That's a video.